So hydrogen has been an important part of the industry for many decades, right? So the utilization of hydrogen is not something that is new. It has been around for some time. However, recently the interest of hydrogen utilization has just been picked up again. And it mainly comes from two reasons. The first reason is that the hydrogen production from renewable costs has been reducing significantly, and it is forecast to continue to drop in the near future. And the second reason is that, with the urgent coming from greenhouse gas emissions from a number of different countries and from, the global effort to produce energy in a more cleaner way, hydrogen has emerged as one of the most kind of potential candidate or re-emerge, if you like, as a clean energy carrier. And as you can see on the slide here, it can be produced from a number of different sources. It can come from natural gas, it can come from nuclear, or even coal. But the most important is that it can come from renewable sources. So when hydrogen is produced from renewables, such as wind, solar, or biomass, the hydrogen would be termed as green hydrogen. And that's why the interest in hydrogen has been picking up recently. So it can be produced to a number of different production pathways, but it can also be used in a variety of different applications. It can be used as a fuel, or it can be used as chemicals. So the fact that hydrogen can be produced from renewable sources, meaning that it would be able to allow renewable sources to even play a more contribution to the energy mix in the future. And that's why I believe to understand a bit more about hydrogen wouldn't hurt. In fact, it would give us a good appreciation of, understand why all the interest had just recently been picked up about hydrogen. So the first thing I want to mention is about the hydrogen abundance theory, right? You might or might not heard it, but hydrogen is the most abundant element in the universe. So by mass, this element comprises 75% of the universe, and it accounts for 90% by volume in the universe. However, on Earth here, it only is the third most abundant element. It ranks after oxygen and silicon, and unlike in outer space, hydrogen on Earth does not exist in a pure form, right? So hydrogen on Earth is always present or exist in a combination with other elements. As a result, if we want to use hydrogen on Earth, first we have to make hydrogen, right? So we have to separate hydrogen from its compound, to separate from other kind of elements to be able to use further. So we're going to talk very quickly about atomic hydrogen. So the atomic hydrogen is the first, or the hydrogen is the first element in the periodic table. Its atomic number is 1, meaning that it has 1 proton in its nucleus. There are 3 naturally occurring hydrogen isotopes. Protium, which is most abundant, only have 1 proton in the nucleus. Deuterium would have 1 proton and 1 neutron in the nucleus, and tritium would have 1 proton and 2 neutrons in the nucleus. In normal condition, hydrogen gas is a stable molecule made of 2 hydrogen atoms, and there are 2 forms of hydrogen molecule exist and depend on the rotation of the nuclear spin of the individual atoms. If they are spinning in the same direction, parallel, then you can have auto hydrogen. But if this spinning or the spinning direction is on the opposite direction, then you have the para hydrogen. So the property of hydrogen that you normally encounter is normally referred to normal hydrogen, which is essentially a mixture of 75 volume metric percentage of auto and 25 volume metric percentage of para hydrogen at NTP condition. So NTP here stands for normal temperature and pressure. So essentially at 20 degrees C and 1 atmospheric pressure. The lower temperature of hydrogen would favor the presence of para-hydrogen. As you can see on the figure on the right hand side here, as you're decreasing the temperature, then the proportion of para and auto-hydrogen will change. And by the way, the temperature scale here is in Kelvin rather than the degree Celsius that we are really familiar with. And I'll talk more about it in the next couple of slides, but here just want to emphasize that liquid hydrogen at 20 Kelvin, which is minus 275 degrees, have mainly made up 99.8% of volumetric percent of para-hydrogen. So the difference in this molecular form of hydrogen doesn't have much to do with the safety of hydrogen, except, well, because there's always some exception, except if you have to deal with cryogenic application, meaning that if you have hydrogen in liquid form, or if you are dealing with cryocompressed hydrogen. When you're dealing with that cryogenic application, then you need to consider the heat, which is an important parameter. The reason is because between auto and para hydrogen, there's a heat associated with the conversion, right? And the heat of conversion is actually an exothermic reaction with the energy. It's about 1.10, the latent heat of vaporization. So the implication of this, auto to para conversion heat is that when you liquefy hydrogen, right? So if you want to, change the hydrogen gas from the gas phase into the liquid phase, then you have to remove not only the sensible and the latent heat of the hydrogen, but you also have to account for the energy or the heat released by the auto and para state conversion. On the other side, if you are trying to store hydrogen, you have to be aware that your liquid hydrogen can be completely vaporized, even if it is stored in a perfectly insulated vessel. So what it means is that your system or your storage system has to be designed in a way so that it can take the heat of conversion away in a safe manner, or at least have to be able to remove the vapor hydrogen in a safe manner as well. And again, I will touch base more on this later when we talk about the expansion ratio of liquid hydrogen to gaseous hydrogen a bit later. So before we finishing the general property of hydrogen, I just want to mention that there are 3 stages that hydrogen can be existed at. So hydrogen in the gaseous phase or gaseous state is a colorless, odorless, tasteless, and it's not detectable by human sense. It has a very low density. The density of gaseous hydrogen at NTP condition, again, normal temperature and pressure condition, is 0.0838 kilogram per cubic meter. If the hydrogen is in its liquid form, which is a clear liquid, then the density of the liquid hydrogen at normal boiling point, so NBP stands for normal boiling point, is 70.78 kilogram per cubic meter. The density of hydrogen, as you can see in liquid stage, is much more higher than in the gaseous stage. And the density of hydrogen can even be increased a bit further if you can manage to bring hydrogen to a slush stage, which is a mixture of solid and liquid hydrogen at the triple point. If you manage to bring hydrogen to this stage, then you can increase the density of hydrogen, in this case at the triple point, to 86.71 kilogram per cubic meter. Now, the couple of things here that I want to point out, the NTP and the NBP. NTP here stands for normal temperature and pressure. So again, that's about 20 degrees C and 1 atmospheric pressure. The normal boiling point is the boiling point for gas at 1 atmospheric pressure. For hydrogen, if you look on the the gas phase of hydrogen on the phase diagram hydrogen on the right hand side here, you would see that the normal boiling point of hydrogen is very low. It's about 20 Kelvin. Right, so let's go back to that. We've been talking about Kelvin scale for a while, and I just want to emphasize that, you know, for temperature, we can use Kelvin scale, and also we can use degrees Celsius scale, and there are a couple more other temperature scale that you can use as well. But we're just going to use Kelvin and degrees Celsius in my talk today. So an absolute zero temperature is a temperature where all the particles are supposed to stop moving, and all the disorder relationship is going to be disappear. And at that state, it's supposed to be happen at 0 Kelvin, or if you talk about degrees Celsius, this would be minus 273.15 degrees Celsius. So what I mean is that if you're talking about the normal boiling point of hydrogen, which is the normal boiling point at 1 atmospheric pressure, or 101.325 kilopascal here, it's going to be 20 Kelvin, which is only 20 degrees above the absolute zero temperature. The bottom line is that the boiling point of temperature is very low, just in the cryogenic fluid. Another point that I want to point out on this phase diagram of hydrogen is that the critical point on the top right hand side here. So the critical point of hydrogen is at 33 Kelvin and 1.3 megapascal. So the critical point is the highest temperature at which the gaseous hydrogen can be liquefied. So it would be the highest temperature that you can turn hydrogen gas into liquid. So if you have the hydrogen gas, say at temperature 35 Kelvin, higher than this, or 40 Kelvin, or even higher, then you cannot just turn the hydrogen gas into liquid just by compressing it. It's not going to happen. All you're going to acquire is cryocompressed hydrogen in the super liquid phase, supercritical phase. So if you want to receive hydrogen in its liquid form, then you have to bring down this temperature to be below a critical point here, which is 33 Kelvin. So another point I want to emphasize on this phase diagram is the triple point, which is 13.8 Kelvin and 7.2 kilopascal atmospheric pressure. So this triple point here is a point where you can actually acquire hydrogen slush, but because of the condition that you need to meet, for example, not only lower temperature, but the pressure that you have to maintain at that condition, like 7.2 kilopascal is really low. So at the moment, the economics of production for hydrogen slush is not available for the day-to-day use. In fact, it only be viable if you using hydrogen for aerospace propellant kind of purposes. So in my presentation today, I'm just going to focusing on the safety aspect of dealing with hydrogen in gas state and hydrogen in liquid state. And specifically, in particular, I'm going to separate these the talk into two streams, as you're going to see in a second. So before we move into that, I just want to put out a very quick slide here, just to summarize all of the important physical and chemical property of hydrogen. So again, in order to follow the presentation, I would suggest you to take a note of this NTP and NBP kind of abbreviation here. So NTP stands for normal temperature pressure. So it's at 293 Kelvin and 101.3 kilopascal pressure. So essentially 20 degrees C and atmospheric pressure. And the normal boiling point here refer to hydrogen at 20 Kelvin and the pressure, atmospheric pressure.